In part 6 of lecture 1, we will discuss counting loops and compound interest. We're going to look at another example. This other example will lead us to look at a few other things as well. Many of you may be familiar with the story about the Dutch buying Manhattan Island for $24. It was actually 24 guilders in trinkets and beads and things like that. And they didn't actually pay the Manhattan Indians who lived there, but the Canarsie Indians who had their summer hunting ground there. But imagine for a moment if the Indians had put that $24 in the bank and had earned 5% interest per year. Now, there were no banks then, so the example is may seem a little unrealistic, but it does show us the power of compounded interest, as you will see. There is no inputs in this program because the values that we're going to be using here are fixed. It's a very rare occurrence, but we'll do it in this case. The output is going to be the year and the principal for the various years over the time. Additionally, we know that the principal started out at $24. Interest will be the interest rate times the principal. And at the end of each year, the new principal will be what the old principal was, plus the interest. The program starts public class interest open brace, and then in a comment we write, calculate the interest that the Canarsie Indians could have accrued if they had deposited the $24 in a bank account at 5% interest. We begin the main program by writing public static void main, and in parentheses, string open close brackets args, and end the line in open brace to begin the main method. Final int present equals 2005. I originally wrote this program a few years ago. Int year final double rate equals 0.05. The present year and the rate for this program are constants. Double interest principal. And the first executable statement in the program, we set the initial principal at $24 by writing principal equals 24 semicolon. Before we begin the loop, we write as a comment, for every year since 1625, add 5% interest to the principal and print out the principal. The loop begins for, open parenthesis, year equals 1625 semicolon, year is less than present semicolon, year plus plus. We will start at 1625, continue until the year before the present year, and we'll add 1 to the year each time around. Inside the loop we have interest equals rate times principal, principal equals principal plus interest. And then to print it out, system.out.println, open parenthesis, quote, year equals, close quote, plus year, plus, quote, backslash t principal equals, close quote, the backslash t again will tab over, plus principal, close parenthesis, semicolon. We have a brace to close the loop, a brace to close the main method, and a brace to close the program. Let's take a look at the output that we'll get. For the first year, it'll be 25.2. The second year, 26.46. And then 27.783. And you'll notice that we get after that a large number of decimal places. As we get near the beginning of the 21st century, the number is in scientific notation. The thing that we can see from this is not the way we expect normally to write money. So we are looking to see if there is a way that we can format our output so it will appear in a way that we are used to seeing it. The method that we have used for printing so far, SystemOutPrintf, is good if we don't need to do anything special to prepare our numbers for printing out. But when you're dealing with floating point values, whether you are simply looking to limit the number of decimal places, or whether you're looking to get it in a particular format like we will, means we need something with a little more of an ability to format numbers, and that is where SystemOutPrintf comes in. It gives us a way to write output that is formatted. In other words, we can control its appearance. We write the method as system.out.printf, an open parenthesis, and the first thing we'll have is what we will call a control string. We'll talk about this in a moment. And then we'll have the first argument, the second argument, and so on. The control string, in essence, is a template. It controls the layout of how we have the text set up. And in it, there will be things that we insert that will be replaced by the other outputs that we're looking to print. You'll see this very shortly. If the only thing I'm printing is literal text, SystemOutPrintf will look a great deal like SystemOutPrintf. And in the example you can see where I'm printing out this is a test, it looks pretty much the same as what we had before, but there is one big difference. SystemOutPrintf will not automatically take us to the next line the way println does. The F stands for format, and in the case of println, the ln stands for line, to print out a line, taking us to the next line afterwards. So, whereas if I had two SystemOutPrintf statements, each of which had this is a test, I would have them on two separate lines. But with SystemOutPrintf like this, I get them all written on one. If I add a \n at the end, so that each one goes to the beginning of the next line, it would work more or less the way we've seen before. I've spoken several times about there being special characters. Let's take a look at a few of these. They all will begin with a backslash. \n is a new line. \b is backspace. That one we don't use too much. \t is a tab. \n and \t for new line and tab are used fairly often. There are a few others. We will bring them up if it becomes practical to do so then. Now, these can appear anywhere on a line. So I could write SystemOutPrintf, this is a test, \n, it is, ! !n. And with one line, I can print out two lines of text in that one command. Specifiers allow us to add text that is not always the same inside the control string that we have. If I put all of the specifiers begin with a %, and they usually will include sometimes a number and then afterward a character telling you which one it is. %d indicates that you are working with integers. Now, it may seem unusual, integers using %d, but the d stands for decimal, base 10, which is what we usually are interested in writing it as. %f is for floating point, and it will work for double precision as well. If I put in the number, it'll tell me how many spaces it will use in most cases. So, %nd tells me that it will print the number in question using at least n spaces. If it needs more spaces, it will throw off the alignment a little bit because it is believed that it is more important to have the whole number there than to preserve the formatting. %w.df is the width. It'll take at least w spaces to print the number, but it will take exactly d decimal places. And we will look at some examples of these in one moment. You'll see here a table with 3 columns. The first for a number, which in the first 4 lines is 182, and the last 3 are -182. Various formatting for printing an integer in decimal format, and how it'll print out. 182 with formatting %2D, we're allowing at least 2 spaces for it. It needs 3, and it will take the third. I jokingly talk about it having sharp elbows. It takes the room that it needs to fit in. 182 with %3D prints the same way because this is what it actually does need. 182 with %5D will use 3 spaces to print the number, and 2 in front of it are left blank. The number in this case is right adjusted. This is the way, right aligned. This is how it normally will handle it. 182 with %7D, again right aligned, will have the 4 blanks up front and then the 3 digits. Negative 182 is printed using all 4 spaces. We remember that the negative sign takes up a full space, as do each of the 3 digits. %5D will give me 1 blank in front, and %7D will give me 3 blanks in front. On this slide, you'll see a continuation of the table. The numbers that we have here are 23, 11,023, and negative 11,023. We started out with 23 using the formatting %1D, and again, since it will allow at least 1 space, we will be able to fit in 23. %2D will again give us 23. This is the exact amount that we need, and it's all fine. %6D, this time we're using periods to indicate the blank spaces along the way. And you can see that I will have both of the 2 digits and the other 4 spaces to the left of the number because this is right aligned. And %8D, and I'll have 6 blank spaces before the 23. Now for 11,023, I have %4D, which fits the number because it makes room for the extra space, for the extra digit rather. And %6D, we have 1 blank space and then the number. For negative 11,023, %6D fits exactly because, again, the negative sign takes up another space. In the case of negative 11,023, you'll see that I have 4 blank spaces followed by the number, 1 less blank because I need an extra space for the negative sign. The table here is a little different because we're dealing with doubles, and there's a fractional part, and in some cases, maybe even sometimes an exponent. But we're not dealing with exponents in this instance. The number in each case is the value e, the base for natural logarithms, and you see it here to 9 decimal places. Now, in the case of %8.5f, I have to have exactly 5 places to the right of the decimal point, and we will round off. Rounding off to 5 places means that I'll have 2.71828. Now, I need a 6th place for the period, for the decimal point, a 7th place for 2, and that means 1 blank space. Now, let's take a look at %8.3f. 3 decimal places, which means it's rounded off to 2.718. 3 decimal places, and the decimal point is 4. The 2 at the front makes it 5 spaces, and that means I have 3 blanks up front. %8.2f means that I'm going to round it off now to 2.72 because I'm rounding up because of the 8 in the other place. That's 2 decimal places. A period, a decimal place makes 3, and the 2 makes 4, and these 4 blanks in front. If I round it to 0 decimal places, I'll get exactly 3 with 7 blanks in front of it. Notice that in this case, there is no decimal point. The last 2 cases, we're going to have 13 spaces. 13.11 means 11 decimal places. Since I only had it to 9, that means the last two are zeros. Now 9 decimal places plus a decimal point is 12, and the 2 at the front, it makes 13. In the case of 13.12f, clearly I'm going to need more room than I'm specifying, but again, sharp elbows apply here as well. We are going to take a look at a revised version of the program. As you can see here, the program begins exactly as it was before. We will not see any changes on this slide. And on this slide, you'll see that there's only one statement that I've changed. Instead of having SystemOutPrintf, I have SystemOutPrintf, and inside the parentheses, I have in quotations at first the control string, year equals %4d. So I'll have the year printed with at least 4 spaces in base 10 format, as we would expect, a tab, principal equals $13.2f. I will allow at least 13 spaces, exactly 2 decimal places for the dollar amount. I now need a \n, so I get a new line afterwards. Printf will not do it on its own. At the end of the line, you'll see a comma, and then the 2 values that are going to be inserted, year and principal. Now you can see the value of being able to format output. The numbers appear exactly as you would expect dollars and cents to appear, and you can easily see the effect of compounding interest over 379 years. This makes it well worth the effort. But the other question that now comes up is, do we really need to show this for each and every one of those years?